Hello. After a long time, welcome to the new class. And today we are going to discuss about Sommerfeld model, but uh, we are going to discuss about Sommerfeld model in a different kind of system. So before starting, because we had a long break, what we are going to discuss about it is a little bit of recap of what we did in the last class. So what we did in the last class is pretty uh, similar to what we will do in the this class. Okay, so we will do Sommerfeld model again. So a brief recap of what we did. We did Sommerfeld model for a free electron, for a for free electrons, or in a better word, it would be free electron gas. So that is what we did for Sommerfeld model. What we did is we took a box, we took a rectangular box of volume V, and we say that this box is empty and there are some electrons filled in this box, and but the electrons can't go outside of this box because the potential is zero inside this box, but it's infinite outside the box. So that is something we discussed. We actually found out what was the relation between the Fermi energy and also the electron density, and we found out that how is the energy quantized and what is the wave function looking like and all. And we also discussed about the antisymmetry condition, or that because electrons are fermions, so two electrons with the same quantum number, same quantum state cannot be like there in the system. So their two electrons cannot be in the same quantum state. So that is all of the things that we discussed. So now what we are going to do is, because in real systems, what we are studying is are not these kind of boxes, but we are studying our crystal systems. So we are not going to deal with these kind of boxes anymore. Let us go back to our earlier episodes when we talked about the reciprocal lattice and the lattice system and the basis and all. So we are going to see that how does Sommerfeld model work out in these kind of systems where we don't have a confined box, but we have a crystal structure where the electrons can be everywhere in free space. So it's a crystal structure. So the electrons can be everywhere. For example, this is a cubic lattice. The lattice can be anything. A 3D lattice can be anything. It can be orthorhombic, it can be hexagonal, so it can be anything. But let us talk about a cubic lattice just for simplicity. And what we have is electrons are free. There is no potential anywhere, but it has what? It has, because it's crystal, it has periodic boundary conditions. Periodic boundary conditions. So, for example, let's say this is the origin, this is the x-axis. So let's say this is Lx, this is the y-axis, this is the Ly, and this is the Lz axis, and this is the Lz. So Lx, Ly, and Lz are the length of the lattice in x, y, and z direction. Here, in this case, for a cubic lattice, Lx equal to Ly equals to Lz, but this needs not to be the case. Or also another thing would be that like Lx, Ly, Lz, they do not need to be lying on x, y, and z coordinates, nor they need to be orthorhombic, orthonormal to each other. There are lattice systems where the angles between these vectors, for example, a more general description would be rather L1, L2, and L3. The angle between these three can be different. So what we will see is, for example, psi of, so we will see that this psi at this boundary should be equal to psi at this boundary. So x psi of x xy 0 equals to psi of xy L2. Uh, is it? Oh, oops, sorry. Let's say this is L2 and this is L2 and this is L3. So this is the z direction, or this is the y direction, this is the x direction. So yeah, we need to basically what we are seeing here is in the xz plane. So x and z would can be vary, but y will be 0. So an x l to z. So that would be this boundary condition. There will be another boundary condition which will say that the boundary this will be the boundary this. The blue boundaries will be equal. So let us write it with blue ink, and what we have is in the yz plane. Now the boundaries are in yz plane. So 0 comma y comma z equals to psi of l1 comma y comma z. So that will be another one. And then we have, let's say, the red, blue, green. Yeah, so let's say the front will be equal to the back. So it will be now the xy plane. So psi psi x comma y comma 0 equals to psi of x comma y comma L3. So these are the periodic boundary conditions. We are not needing the psi equals to 0 at the end of or the boundary of the box anymore. What we are needing rather is something different, and we are needing that the wave function should be equal at the opposite boundaries, because these boundaries are equivalent in a periodic boundary condition, in a system which has periodic boundary conditions. So for example, we impose these laws, we impose these boundary conditions. We already know that the general solution of the free electron model is given as this. So that is how the psi k of r is given. This is the general solution. We will need, and actually the more general solution would be psi of r would be a summation over a lot of k's, because each of k is a good solution. It's a good solution. So this will be the most general solution. Or let's say there are also coefficients ck. So these are the like general solution. So we need to actually impose some constraints on ck to see that, to make this wave function follow these boundary conditions. So if you do a little bit of math, then what we will see is uh, that this boundary condition, when you impose this boundary condition on this wave function, what you get is the case, all k's are not allowed. The allowed k's follow kx lx equals to 2 pi nx by lx. So I am sorry, 2 pi nx. Yeah. So I am again writing it as lx, ly, and lz. That might not be true. So that can also be written as k1 l1 equals to 2 pi n1. So that is these things are like strictly applicable for a cubic system. If you don't have a cubic system, then these relations can get a little bit more complicated. But just to get a general idea, a cubic system is the best system to work in. So ky ly equals to 2 pi ny, and kz lz equals to 2 pi nz. Okay, so this is what we will get for the periodic boundary conditions. So if we write it in another way, in a more compact vector way, so what we will get is 2 pi nx by lx x cap plus ny by ly y cap plus nz by lz z cap. So these are the form, these are the case which would be allowed by the system, and the other case would not be allowed. So basically what we will get is a quantization. What we get is a quantization of case. Okay, so what are nx, ny, and nz? These are just integers. Okay, so these are the k's which are allowed, and these are integers. So as we can see that these k's also form the reciprocal lattice that we discussed earlier. So if you remember the reciprocal lattice that we discussed earlier, this was the same relation we got from a lot of rules. We got it from Lois condition, uh, and we also got it like indirectly from Bragg's law. So this condition is very well known to all of us right now. So yeah, so the k is given, and now yeah, like we can make a grid of this case. So let's say this is a grid which has like a lot of points. It also makes a lattice. The k's also make a lattice, which all we already know is called the reciprocal lattice. Yeah, so I will make the grid. So yeah, so this is kind of the grid. Basically, it's also a coordinate system where the x-axis is given as a kx, the y-axis is given as ky, and the z-axis is given as kz. So yeah, this is and also E is equal to h square k square by 2m, as we all know, for free electrons. This is only for free electrons. So h square by 2m kx square plus ky square plus kz square. Okay, so it's a sphere. It's a sphere in the reciprocal space, in the k space. So it's a sphere. So this is what we got for the periodic boundary condition. So this is what we got for how Sommerfeld model works in a crystalline system, where there is periodic boundary condition, where there is repetition, there is like symmetries. There are symmetries in the system. Okay. Okay. So now we want to proceed further. This is like a sphere, and then again we want to find that how will the relation between the Fermi energy and the total number of electrons, these kind of things, what do they correspond to? So these things we have to, like, bit by bit we have to build up. So and how we can do that, we will take the same approach. So just these are the side notes. The momentum operator is given as this for a system. For free electrons, if psi k is e to the power I k dot r by v, then the momentum is given as hk, and v is given as r dot, which is given as so there is a formula which is well known, which is given as this. So this is a well-known formula for the time evolution of any operator. So the velocity operator for a free electron is given as this. These are just two side notes which may or may not be useful in the future, but this is more useful. This is often called the relation between momentum, electronic momentum, and the k vector, right? So this is important. Now what we will do is we will think of Lx, Ly, Lz to be very large. So now if we have the grid of k, so now we see that this like the energy sphere, the surfaces which have same energy are spheres because of this equation, because of this equation, Oops. Because of this equation, right? So because of that, what we have is like these are like spherical isosurfaces. These are also called isosurfaces sometimes, which have same energy. These are called energy isosurfaces. And in this case, what we will see is now we want to convert these summations over integrals. So we know that there are now only discrete kx and ky's discrete k points available or allowed in the system. But what if we happen to allow these points to be very closely packed, because of Lx, Ly and Lz are very large, and uh, and this is the vectorial form of k, which is inversely proportional to the lengths. So if the lengths are very large, then these discrete points will be very closely packed together, and for most practical purposes we will be able to take these as a continuous bunch of points. So uh, every point has how much volume. So for example, let's say we take a unit cell in this K space where the lengths are given as 2 pi, and at each of its corner there are some atoms. So there are some k points, allowed k points, and so the length of these sides are given as 2 pi by Lx, 2 pi by Ly, and 2 pi by Lz. Okay. So how many k points are there? There are 8 into 1 by 8 equals to 1 k points, because there are 8 red dots, but each red dot is shared between 8 such unit cells. So for example, this dot, it is shared between 8 such unit cells. I am only drawing one unit cell, but there are, for example, just to not make it too much clumsy, I will show. There is this unit cell, there is a unit cell here, there is a unit cell here. So these are 4 bottom, 4 top. There is a unit cell here. So there are 8 unit cells which are sharing this red k point. So 8 8 so each unit cell is getting 1/8 of each of this red dots. So there is only one k point effectively in this whole unit cell. Okay, so if that is the case, then what we have is we have 8 pi cube by Lx, Ly, Lz volume hosts 1 k point, right? So 8 pi cube by V dk will be the number. Oops. So then one volume. So it's a basic unitary method. So the one unit of volume will host V by 8 pi cube k points. So dk volume will host V dk by 8 pi cube k points. So that is a very important result, because that will allow us to calculate other quantities later. And so basically this means that in the k space, in each dk volume there will be this much amount of k points available. So now we want to look at the ground state, like what will be the ground state looking like. So this is because we are moving towards the same Fermi energy, Fermi momentum, and density of electron relations that we derived for the box. So the same thing we are going to derive here. Okay, so first let's say we do Fermi energy. Okay, so we want that how much will be the Fermi energy. So as we can see that the whole thing is confined into a sphere, right? So let's say this is the sphere, this is called Fermi sphere, and this is the Fermi surface. So this kf is often called Fermi momentum. Kf is often called Fermi momentum, the largest like the largest k magnitude in which you will find occupied states. So why is it called momentum though? Because we already discussed that this is what we get, but often in atomic calculations the h bar is taken to be 1, so kf itself is called momentum. So how many electrons can be there total? So 4 pi kf cube volume v by 2 pi cube, because we discussed that in each unit volume there will be v by 2 pi cube amount of k points available. So these many k points are there in this sphere, and in each k point there are two electrons, because it is like plus and minus. So like sorry, it's plus spin minus spin, like up spin down spin. So then each k point there are two electrons can be there. So the total number of electrons will be v kf cube by 3 pi square. So that will be the total number of electron. Okay. So now what will be the density of electron? Density is given as Ne by V, which is given as kf cube by 3 pi square. So it's a very important result again. This is kf cube by 3 pi square. So this is an important result. This is the relation between the Fermi momentum and the electron density. Okay, so let us go forward, and what we will see here is now what will be the Fermi energy. What is the relation between Fermi energy and Fermi momentum? It is obviously given as this, as we saw earlier. So we have 3 pi square rho e whole to the power 1 by 2 by 3. So again we get something very similar of what we got earlier. So uh, yeah, we also got this result for the confined box system that we were doing, that we were calculating. So it's exactly the same thing, and we saw that even if we change the condition, like even if we change the boundary condition, what we get is exactly the same. The relation between the Fermi energy and the electronic density, it has become the same thing. So it is having the same relation. So this, by the way, if we it can be rigorously proved that this is a general equation. This is a general relation independent of boundary conditions. Okay, so now we get the relation between Fermi energy and electronic density. Okay, now again we take the Fermi velocity to be hkf by m, which can be given as what was it, 3 pi square rho e by 2 to the power 1 by 3. So that can be given as the Fermi velocity. Okay, so now we want to see what is the total energy, total ground state energy. So for that, what we will do is E is equal to, you will have to sum over all the electrons which are inside the Fermi energy, right? So we will have to sum over, for example, this. So basically k h square k square by 2m, where k is less than kf, into 2, because there are 2 electrons per site, per site, plus up spin down spin. Okay, so now what it's been done is, because we already assume that the k space is very closely packed, so we will consider the case to be a continuous variable. So what we will do is we will change it into an integral. We will write it to be h square k square by 2m into 2, and we will actually multiply it with for example something called um, so when we convert from summation to integral, then there are some rules. So how we can do that? Basically, we will say that how many we will multiply with it with this, because if you remember that how many k points in dk volume is given as this. So this is what we multiply it with. So when we do that, what we will get is this dk, by the way, for a spherical system will be given as 4 pi k square dk, but this k is no longer over the vector, but it's over the magnitude. K to the power 4 dk. Okay, so when we do that, what we get is v h bar square by 2 pi square m k to the power 5 by 5. So 0 to kf, so k to the power 5 by 5. Okay, I think that's correct. Yeah, so if we do that, then we can obviously we can very easily relate it with the Fermi energy, uh, and what we will get is this is what we will get if we do the math. So yeah, now uh, basically what it tells us that if we took the classical model, then we would not have got this thing, like, because we can see that even in the ground state the total energy is not zero. The total energy is not at all zero. So there is a significant amount of total energy that the ground state has because of the Fermi-Dirac distribution function, because the lower states are already being filled with electrons, so the rest of the electrons have to go to the upper and upper states and fill up till the Fermi energy is achieved. So we see that, like, the ground state of a Fermi gas has some energy. It has some energy. So coming to some more practical, so that was the motivation of all of this. It is just to understand that how the Fermi-Dirac distribution fundamentally makes the Sommerfeld model so much different than the Rude model, because the Rude model is like, it is extremely classical and it will give you like absurd results because of these properties, these quantum statistics, that these two electrons cannot be together, these kind of things are not taken care of. So sometimes there is a thing called a Wigner-Seitz sphere. So what is a Wigner-Seitz sphere? Wigner-Seitz sphere is like a sphere which only has like one. It has only one lattice. It has only one lattice point. So that is what is called a Wigner-Seitz sphere. So what it is given as? It is given as 1 by the density of electrons will be given as 4 pi, let's say rs cube, where rs is the radius of the Wigner-Seitz sphere. So rs is actually a very important quantity. Uh, it is even used nowadays. It was defined in like 1930s, but it's used nowadays also to characterize like various systems. So so we got that this is equal to rho e, and by doing this, by comparing these two things, what we will get is 4 pi 4 by 3 pi rs cube is equal to 3 pi square by kf cube. So rs cube is equal to 9 pi cube by 4 by kf cube, and if we take the cube root on the both sides, what we get is like, oops, it's not pi cube, it's pi, yeah. So if you take the cube root, then it will get something like 1.19 1.919 divided by kf. So that is the relation between the Fermi momentum and the Wigner-Seitz radius. So sometimes this quantity called uh, Rs by A naught, where A naught is the Bohr radius, which is like around 0.529 angstroms, is like relate. It is taken as a dimensionless quantity. So this, let's say this is called R Wigner-Seitz. So sometimes this is also denoted as R naught, like just to be on the safer side with notation. So this R naught by A naught, or this R Wigner-Seitz R naught by A naught, this is a very important quantity. This is used for characterizing metals. For some metals, for some materials it will be large, for some materials it will be small. And also the de Broglie wavelength, or the like characteristic wavelength of the Fermi electron is can be calculated easily as 3.27 into R naught. So again, as we can see that this has like some good implications for monovalent metals like sodium. The R naught is large. For some materials R naught is small. So there are like tables, and these tables are for calculated R naught. These tables are very important and very useful for people who are dealing with materials. A large R naught means that the density is low and the interactions will be low, but for strongly correlated materials R naught will be slow, so interactions will be large. So yeah, that is the kind of whole message of this whole class. So I think, yeah, we have discussed whatever we planned. We discussed, and we have gotten hold of the Sommerfeld model and how it looks in a periodic boundary system, a system with a periodic boundary condition. We saw that this is the general equation, and we impose the periodic boundary conditions to discover that the k's are indeed quantized, and also the k's are indeed quantized. And then we discussed about some operators, and then we discussed about how does the electronic density relate to the Fermi energy and the Fermi momentum. And we discovered that it is exactly the same as the last class, where we dealt with confined boxes, electrons being in confined boxes. And we also saw that the Fermi gas has a considerable ground state energy. And we talked about Wigner-Seitz sphere, and there is a thing called Wigner-Seitz cell also. We will discuss it later, but we talked about Wigner-Seitz sphere and how the parameters of the Wigner-Seitz sphere relate to the Fermi momentum or the Fermi wavelength. So this was all that I wanted to discuss. In the next classes, we will be going to discuss that how does this model react. All of this that I am being discussing is like zero temperature. It's zero temperature. But what happens when we excite the system so that some electrons which were like near the Fermi energy, they get excited into unoccupied states? So that is when we will get electricity. That is when we will get thermal transport. That is what we will discuss in finite temperature systems. When we increase the temperature due to thermal excitations, there will be some electrons which will be jumping from the filled states to the empty states. So that is what we will be going to discuss in the next class, and we will be sticking to Sommerfeld model. So after that, we will discuss that how can these models be more and more generalized uh, for the periodic systems. So until next class, thank you and best of luck.